Next, we would like to invite on stage Professor Memon with a slightly mysterious title of Listen to Your Data. Please welcome him to the stage.
Thank you. All right. Can everybody hear me? Okay, very good. All right. So I'm Atif Memon from the University of Maryland, College Park. I work with several companies in the Bay Area, so I work on areas of test automation and scale. I found that we are spending more and more effort and time on testing, both in terms of developers and testers' time in writing the manual test cases and infrastructure to run those test cases. I've also found that many companies, we have this attitude of running the test cases, finding out which ones failed, and going back and fixing our code, and then throwing away all the results, and then going to the next test cycle. Because we spend so much time and effort on testing, we need to get away from this mode. Instead, what we need to do is we need to start keeping histories of all our test cases so that we can make some sense out of them over a longer period, improve our testing processes, and inform other stages of the development pipeline so that we can improve everything with the test results. So I'll tell you how we're doing that at Google. So first slide is acknowledgements. All this work that I am presenting was done at Google during my sabbatical last year. And everybody mentioned on this slide has contributed in some way to the ideas and discussions. We are fortunate to have John Miko also in the audience here today. And he is here for two reasons. One is to make sure that I don't say anything wrong. And the second reason is to answer all the difficult questions that you may have. All right, I'll answer all the easy ones. All right, so Google is actually the perfect place for this kind of work, where I wanted to look at how do you take testing at scale, and how do you reduce the resources that we are spending on testing, how to make it more efficient, and how to use the results to empirically study the test cases and inform other parts of the development pipeline. Testing plays a really important role at Google because one is that they have this insane single monolith code where developers are making changes every few seconds. Everybody is working on head. There are no branches. To maintain sanity, the TAP team is continuously doing continuous integration and making sure that things don't break. All right, so there are a couple of good resources mentioned on this slide. I encourage you to watch those videos and read the papers. They basically tell you why Google maintains a single code repository and tells you about the TAP system. So let me give you an overview of how TAP currently works. And so on the x-axis here, you have what are called change lists. And change lists, you can view them as commits, right? They are code commits that are coming in. And on the y-axis, I have 14 test cases. I will use the term test cases and test targets interchangeably. At Google, we call them test targets. For the sake of this presentation, they're identical terms. So I have this change list. Somebody has committed code. There are a bunch of files that have changed as a result. Here are the test targets that are affected by this change, which means when I look at this dependency graph on this side, that lowest node there, that's one of the files that got modified by this change. And I'm going to go traverse this dependency graph in the reverse order. And if I encounter any test case on the way, that is going to be a test case that's affected by a change, which means that because of this change, the outcome of this test case could fail, could change. It could pass or it could fail. So I'm going to use this reasonably intelligent method to select a subset of my test cases. And believe me, there are lots and lots of test cases at Google. So you need to select a subset. These are called affected tests, right? So changes are coming in, affected tests are getting selected, and we are going to be running these test cases. Now, if I show you what happens at Google scale, these are the changes that are coming in, all right? Every few seconds, there's a change coming in. And here are the test targets that are being affected. The y-axis, because it's such a massive scale, it's all logarithmic scale. So you see one of the numbers here, 1.4 million test cases were affected by a single change that's buried somewhere here, all right? So it's a massive scale, and this is in 2.5 hours. Okay? So things are not going to scale. We are not going to be able to run all affected targets for every change. So we have to do something better. All right. So what they do is they have this concept of called milestones. What they end up doing is they postpone testing. All right. So they realize that they cannot test at this point. So they carry this debt forward. This is what I call their debt. And all the red nodes are all the test targets that are affected, and I'm carrying them forward without running them. And at some point I decide that I'm going to run them, and I'm going to call that cutting a milestone at that change list, right? So I may have gone over thousands of changes, and because now I have compute resources, I'm going to cut this milestone. All right, so cutting a milestone means I'm going to pick all the test cases that were affected, their rightmost version, right? So this is the change list, and here I'm going to run this test case on this version. Sometimes change lists come out of order because it's a massive infrastructure, and so those also get incorporated into the milestone. So I run my test cases, I get some passes, I get some fails, so I have those red are failures and the greens are pass test cases. Because I've postponed my testing so much, that red failed test case that you see there, that failure could have been caused by any of these changes that were done along the way. So we have tools that are called culprit finders that go through that list and figure out who broke the build, right? I'll talk a little bit about that too. All right, so an average tap day, we're running 13,000 code projects, okay? We're running 800K builds, 150 million test runs. That's a lot of infrastructure that's being used for testing. Tests are distributed across many machines, so there's sharding. One machine obviously cannot run all this, and they're collected and they're presented, okay? How long does this take? Let's measure the latency, all right? So I have code is checked in at this point, and I have my result available at this change, CLN. This is where I checked in my code. Here is where I see my result, all right? How long does it take? I'm going to measure the latency from this commit to the obtaining of the results. I looked at a sample of 636 edges. An edge is a test case that went from pass to fail or fail to pass. To me, that's a very important, these are important test cases because they either indicate that something broke or I fixed something and it worked. So the latency is 4 hours average, but if I show you the distribution, you see that many of them took a couple of hours. So from committing code to getting my test results, I'm spending a couple of hours, which is not bad, right? So every developer knows what's going on within a couple of hours, but sometimes it takes 8, 9 hours also, right? So that's a long time. All right, so what are the challenges for running this kind of thing at scale? One is there are too many tests. Even though we are selecting intelligently only the affected test cases and we are postponing our builds, we still have too many tests. And as our code base grows larger and larger, we might be unable to scale. So can we do something smarter? We have flaky tests, all right? You already know what a flaky test is. We have the issue of culprit finding. We need to know whenever a test fails, who broke the build. And then we also need to understand this interplay between pre-submit tests, post-submit tests. When a test case passes or fails at pre-submit time, what are the implications for post-submit time? Do we need to run the same test cases again? What should we do? Right? So we need to understand empirically what all these interplays look like. All right, so our scientist here, who is actually a princess drawn by my daughter, is telling us to listen to the data, all right? If we can listen to our data, if we can perform some statistical analysis of the signals from the changes, right? So I have 3 things to look at. I have my changes, which is coming from the code. I have my test cases, and I have my failures. If I can relate these three things and create statistical models, I can perform 4 of these things. And I'll talk about all of them. I can do smarter test selection, which means of the affected test targets, I can select a subset. I can do automatic detection of flakes. I can do faster culprit finding, and I can also inform developers by giving them customized IDE alerts while they're writing test cases, telling them about what may go wrong because of what we've seen in the past. All right, so what does it mean to listen to our data? Let's look at our data here. So I have 8,842 changes going over 5.5 hours. The y-axis here is showing us how many test targets were affected. Right? So you see very quickly, after a few changes have happened, I have already affected, let's say, 1.5 million test targets. And that number keeps growing and growing and growing until I get to 2 million after 5.5 hours. Right? Let's look at this picture in a slightly better way. These are the individual test targets that I showed you before. Right? Even though I am at 1.5 million here, and this change also affected around 1.3 million, it did not affect, it's actually 1.4 million, it did not affect too many new test targets, only 27. All right? So that means there's considerable overlap between this list and this list here. That means our milestone build idea is working well because there's lots of overlap, and we are postponing testing, and that we are saving resources on that. Again, here I have number affected 1.4 million and unique affected is 4. So there's lots of overlap. The other thing I want to show is I quickly reach 95% of my affected test targets, like 2.7 million. I quickly reach 95% at this point. And then if I reboot my list, I again, within a few changes, I get up to 95%. So I quickly go through all of my test targets within a few hours. Okay? So there's lots of overlap, and I am affecting many of my test targets continuously, all the time. All right. Frequency of target overlap. So this is a histogram, and the y-axis here is showing you the count in thousands. All right. So the first column is saying that 151,000 test targets are affected only once. All right. If you look at this in logarithmic scale, you see a much clearer picture. You see 749 targets are affected 289 times. Yet, TAP treats all of these test targets the same. Okay? A test case that is affected 749 is affected 289 times versus 1 time is treated the same by TAP. Should it be treated differently? What do the empirical results show us? Right? By the way, this data is from 5.5 million unique test targets that were run over a period of a month at Google last year. All right. Again, here you see that this vertical line shows you that 50% of the targets were affected fewer than 14 times, and 75% were affected fewer than 46 times. Okay? Again, should we treat them differently, or should we treat them the same like how we currently do? Let's look at the test outcome distribution. Again, this is log scale. So you see the difference between passed and failed. It's several orders of magnitude, right? In fact, if I show you the next slide, you will see that failed in terms of percentage is only 0.4%, and passed is 48%, right? So the number of failures that we are seeing at every run is a tiny fraction of the total test cases. Let's look at this in a slightly different way. Of my 5.5 million test cases over that 1 month period, 5 million never failed even once. Right? They only passed, or passed at least once, never failed. Right? So that's 5 million of them. a small fraction never passed, failed at least once, which are not, that's not very important for me. Skipped, I don't really care about too much because those are labeled as skipped. Passed at least once and failed at least once is only 115,000. So these are the ones that passed and failed, and these to me are the interesting ones, right? Of these, I find out that 46,000 and some are flakes, right? So I get rid of those, and I'm left with the most interesting ones over that 1 month period are 68,000 of the 5.5 million. Now, granted that these 5 million play some role in giving the developer confidence that things are working well, but these are the ones that I am most interested in going to the developer and saying that you broke this build or you fixed it. All right, so we care only about the edges. In my research, I've cared mostly about the edges, which are things that go from pass to fail and fail to pass, right? So I'm going to call this an edge. I'm going to call this a negative edge that goes from pass to fail, positive edge that goes from fail to pass, and so here I have 3 edges. And in my data, I have 500,000 positive edges and roughly 500,000 negative edges, right? So total number of edges I have is 1 million. All right, so how can I first apply my statistical analysis to do smarter test selection? Right? So remember, I have 3 things that I want to look at. I have the code. I want to extract features of the code. I have the test cases. I want to extract some features of that. And I want to extract some features of what is common or what are the relationship between the test and the code. So this is again the same picture that I showed you before. This is the reverse dependency graph. Here I have the code that is changed, and the test cases are the ones that are encountered on the way from the bottom node all the way to the top node, right? Any test cases that I encounter are the affected ones, right? I'm going to start modeling the distance between this code and the test case. So for example, the distance between this node, the shortest distance between this node, which is a test, and this node, which is a Java file, is 4 because there are 4 arrows, red arrows here. I'm going to call that min dist, and I'm going to measure that as a distance between my code and my test case. So in Google, most of the distances roughly fall between, let's say, 3, 4, and 10, but they also go as high as 40. So when I modify my code, I have some tests that are at the distance of 40 that are also being affected. So they are really far away from the code. Are all these tests really necessary? So my hypothesis was that the test cases that are closer have a much better, are much better indicators of a failure. So empirically, I showed that test cases that lie from roughly 5 through 10 are the ones that can catch most of my bugs, okay? And anything beyond 10, I can completely ignore. And in this particular data set, I was actually, there was not a single failure that was caught by test cases that are beyond 10 distance, right? So the closeness between the code and the test case played a big role here. If I was to simulate this and show you how much effort and time I can save, I'm only going to run all the test cases that are below min dist of 10 or equal. I can save quite a few resources, right? I'm only running 58% of my test cases. And I'm finding all the same bugs that I found before using 100% of the data. So that's a great signal to reduce the test space, okay? All right, another signal is the code modification frequency. Code that is modified more frequently is more likely to fail than code that is modified less frequently. If we think about it, it's like, oh, isn't that kind of obvious, right? But this shows you that it actually does happen, all right? And so you can use that as a signal which says that if you wanted to prioritize your test cases, you could say that code modified frequently is more likely to cause breakages, so let's test that first, or let's prioritize the test cases that way. File types, all right? If C++ is your favorite language, I'm sorry. C++ is more prone to breakages than Java. As we see here, this red part is failures, and these blue parts are passes, and I've divided them into to show a percentage. So you can see that Java lies somewhere, where is it? On the right. So being on the right is a good thing for Java, right? Being on the left is a bad thing. And the frequency of your test cases is shown by, of your files is shown by the green curves, right? This raises lots of questions. Why is Java doing better than C++? We can all guess. It requires lots more research, but this is the preliminary result, right? Okay, authors, people who commit code. Some people are bad at committing code compared to others, all right? So user ABZ, 31% of the time, whenever this user committed code, they broke it, okay? So certain users or tools are more likely to cause breakages, all right? I'll let John decide what to do with these people, but I'm not. Okay, this is an amazing result, and it needs to be interpreted properly. So code that is modified by multiple developers over a time period. So let's take a week, right? I have code that is modified 15 times, and I modified it as the only author, as opposed to code that is modified by 15 different people, each modified it once, right? Code that is modified by 15 different people is almost guaranteed to break, as opposed to code modified by a single person, okay, 15 times. All these curves go down at 2, which is amazing, which kind of shows that code that is modified by 2 people, different people, is less likely to be buggy compared to code modified by a single person, right? Again, why does that happen? We can all hypothesize, and it requires more research, right? You will see that with each of these slides, I'm basically telling John that I need to do more research, right? So he needs to keep me on. All right. So that tells you something about how to prioritize your test cases based on types, change author frequencies, code modification frequencies. Let's see how we can apply this to flake detection, okay? So same thing. I'm going to show you some of the same plots, but I'm going to have different messages coming out of it. By the end of this talk, you would have seen each of these plots multiple times, and you'll be sick of them. So here are results that how we see them at Google. The red ones, Fs, are failures, obviously. The green ones are passes. And the other ones in between are the ones where the test was affected but not executed for various reasons. So here you see that the Fs are nicely, cleanly clumped together, and the passes are all in one place, whereas they are all interdispersed here, mixed together. Okay? It turns out that the above one is a flaky outcome, as opposed to this one, which is non-flaky, right? So we'll see what the implication of this is. But let's see how serious flakes are, right? When I started my research, I was told that at any test run, 1% of the test results are flaky, okay? Which to me was like, it's not that bad. If I do my analysis of prediction, flakes will just add some noise, but not too much. But I found out that if you looked at the edges of the transitions from pass to fail and fail to pass, 85% or 84% are due to flakes, right? That means whenever you see a test case go from pass to fail, and if you looked at the results, 85% of the time you'll say, oh, that was because of a flake. And only 15% of the time it's because of a real failure, right? So that's really bad, okay? In case, this is just a curious student, and this is our scientist princess here. All right. So what is the message here? Is that very small percentage of test cases are flaky at any run, but they lead to majority of the edges, okay? And if you really think about this, it makes sense, because a test case that goes from pass to fail at every change because of flakiness is adding lots of edges to your data. All right, so now I'm going to show you the same graphs that I showed you before, but I'm going to repurpose them for flake detection, right? Because each of these signals can be used for automatic flake detection. So for example, this one, test target edges that are farther than of a distance of 10 are highly likely to be flaky. Because remember, we said anything that is within 10 is more likely, you should prioritize those, and those are the test cases to run. But anything that's farther away, they're not likely to be failures, they're likely to be flakes, right? Again, file modification frequency. Failures associated with frequently modified code is highly unlikely to be flaky, because those are the failures those are the frequencies that were more likely to cause failures, right? So I'm just flipping the same charts, but I'm showing you different messages here. Failures associated with config files are highly likely to be flaky, right? Because config files are at the very right and all of them passed, okay? Failures associated with author product 1 release is highly unlikely to be flaky. Okay? Product 1 release is here because 92% of the time product 1 release was caused failure. So you can see how I can repurpose the data with the same with different messages. All right. There are additional signals that we had for automatic flake detection. One is that number of edges. So if I see more edges in my test result, that test case is more likely to be flaky. And that makes sense. If you look at this, I'm showing you number of edges on the x-axis and the percentage of flakiness versus non-flakiness by using a golden, what do you call that, an oracle, which tells you whether a test case is really flaky or not flaky. I'm going to show you how that changes. So as the number of edges increases, you see beyond, say, 140 edges, these are all flakes mostly, right? So flakes are more likely to have edges. So if you want to detect, if you wanted to go through your test cases, and if you just want to look for edges, and test cases that have more edges, you probably find out that they are more flaky, all right? So that's an easy way of detecting flakes. All right. Then we had flakiness score, where we defined a vector which was one or more failures, followed by anything, followed by one or more pass, followed by anything which is not a failure or pass, and followed by a bunch of failures. If you extract these patterns from your pass and fail results, and you come up with a score of number of vectors that you extract which match this, and the length of the vectors, it gives you a really strong indication of whether a test is flaky or not. And when we applied this is very fast. You can actually do this computation very quickly, and you find out that they confirm with what we found to be truly flaky. Okay. All right. The histories. Think about this. I have 2 test cases. Or in fact, I have like 8 test cases. These test cases, T4 and T6, have identical test histories, all right? Similarly, T2 and T3 and T5 and T7 have identical test histories. The first test case, T1 and T8, have different test histories. Now, if you think about this, test cases that share test histories with others are less likely to be flaky, all right? Because flakes happen randomly. They don't happen with a certain pattern. So we wanted to explore that, and we wanted to see how that would plot. So I'm showing you sharing on the x-axis and number of edges on the y-axis. And here I'm just going to quickly go through this and show you the final result. So here, sharing is all 0. And number of edges in the test case, it goes up from 1 through 1,000. And the red things are flakes that are really flakes, and green are not flakes. So you see all of them have clustered to the left, right? Which means test cases that don't share or share with a single test case are more likely to be flakes, right? So you can actually see a very clean separation between flakes and non-flakes, right? I'm happy to discuss each of these slides with you in more detail after the talk. All right, so that's flakiness, right? Okay, so we also want to get to a point where we can predict whether a test case is going to be flaky or not, and we will look at multiple signals. For example, what is in the test case code, all right, or whether the code is multi-threaded or not. So we'll extract some features and we'll try to predict even before running a test case whether it's flaky or not. So that's something that we intend to do in the future. All right, so I want to repurpose all of my statistical analysis for developers. I want to show them things like you're modifying code that was recently modified 41 times. The probability that you may cause a breakage is 75%. All right, so you're modifying code, you see this alert, you're like, I'm going for lunch. I'm not even modifying this code anymore. Right? But you can take some action. You can maybe run more pre-tests, or you can ask somebody else to look at your code, do better, maybe do pair programming, or call the other person and ask them what they've done. You're modifying a file type that is known to cause this many percentage of breakages. We recommend a more thorough code review. All right, so developers get informed about what's been happening, and this is all you're getting this for free from your test data because of the analysis. All right, unfortunately. All right, and then impact on bonuses and all those such things. Okay. This one I think one could take very seriously, right? If I'm modifying a file and somewhere on the right-hand side of my IDE I can see that this file was modified so many times in the last week, maybe I'll be more careful. I'll maybe contact the developers and all. Okay, so I can do all that. So now, if you think about the culprit finding issue that I talked about before, culprit finding is really you have a failure here, and you want to go through this vector of changes and identify who broke the build. That's the culprit finding problem, right? The problem that I've spoken about until now is I have a change list and I want to find which test targets are most likely to break. This is the same problem, but we're flipping it around. We have a single failure and we want to go through a vector of change lists as opposed to going through a vector of test targets. The relationship between the test target and the change list still stands. Whatever relationships we have found before, they still stand, and they will help us pinpoint the change list which caused the breakage. So for example, something that's closest, the distance from this test target that failed to the change lists, the closest one is more likely to be the cause. Most frequently modified, same signals that I discussed before, file types, all right, change list author, our favorite, and multiple developers per file. Okay, so the same things you can repurpose, and you can do better tooling around those. Right. So concluding, large software companies face problems with scale. We've all seen that. Everybody is worried about software testing and scale. All right, there's a huge amount of test data. Unfortunately, some of the companies I've talked to, they don't maintain their test data. Google has been amazing that way. They just threw like 2 years of test data and said, find something. But some of the other companies, you'll be surprised, they don't even keep like a week worth of test data because they say they don't have storage. Like, I can give you a disk. I can give you 25 terabytes, just store the test data. They don't want to do it. So mining of test data is likely to yield significant gains in efficiency. And I think what we've shown is just the tip of the iceberg and what you can do, but there's much more to be done. All right. Acknowledgements, same acknowledgements that I had before. This was all enabled mostly by TAP at Google. And illustrations of the princesses were by my daughter, Annika. All right, I will take questions. And John is also here. So give him all the hard questions and give me the easy questions. John, do you need a mic?
Hi, I'm Tom from LinkedIn. Couple of questions. First one is, when you're taking your sample set, a lot of those tests are running against different versions of the software. How do you, when you're determining flakiness, how do you know it's it's not the same data that you're testing across time. How do you, if it was the same test against the same change set, you would expect to see a certain consistency of flakiness. But since these tests are going, they're being tested against different versions, they could be versions that never happen, right? Do I have that correct? So how do you make sure?
A hard question or an easy question?
This sounds like a hard question.
Okay, so basically, we make a simplifying assumption that if a test transits up and down quickly, and it's not persistently broken, that it's flaky. And we can observe it over a long enough period, even with the changing software underneath, to be able to devise the signal. And Atif very successfully did that. He showed that in his data. Also, it's also true that if we skip over 5 changes and it got broken and fixed during the 5-change window, we won't notice that it ever broke. And so we don't even detect that maybe some of the stuff that we didn't run actually broke. But in that sense, the developers don't really care because we've given them a signal at the next CL that it was all good. So whatever it was fixed. So I guess between those two things, we kind of get to a place where we're pretty confident that we can observe flakiness even through the changing of the system, and that we can sort of make a few simplifying assumptions that turn out normally to be working for us. If we went back and actually ran every single one of the things in Atif's data, it would cost lots of CPU resources. Maybe we would find some more data points that he could use, but it hasn't rendered the data we already have useless. Let's put it that way.
Right, and the second question I have is more about the developer action. How do you turn, this is very likely to be flaky, to a developer actually addressing that and changing the test?
Oh, that's a very simple thing. We have a thing that's kind of like what they talked about in their system. It's kind of, it's one of the reasons I'm here, is because I'd like to be able to collaborate more on some of these ideas, but we have a system called RoboSheriff. What it does is if a test gets more than a certain level of flakiness, it gets pulled from the build and quarantined, much like they do. And a bug gets opened to the responsible developer to go fix that problem or delete the test or whatever. And that's how we do it. We automatically quarantine the test and open a bug, and then the developer gets the bug.
A non-trivial number of breaks that were shown in the chart were related to content files like waves. Do you provide any guidance to test authors on how to make their tests more resilient to content changes?
That's a really good question. I'm sure quite a few of those content files were like golden files for the test or whatever. Centrally, we don't. In fact, our test execution system, the one that I run, is very agnostic in terms of procedures or policies for the most part. So I say that we broadly do anything there, or that I'm aware of specific instances. I'm sorry.
So in the world of A/B testing and version testing, I am very fascinated about the flakiness score. But my question is, how do you tag data relevance, and when does data go stale? So when the culprit finder goes back, is there a tagging between two similar data that should help derive the next test consequence? Or because with A/B testing, every version is unique?
Is data that goes into a test? Is that, so what do you mean you say data? Do you mean data that is consumed by the test when it runs?
Not just, so A/B test would like fluctuate with the user input. So
right.
That would be data going into the test.
Correct.
And listening to this data of the test, that will group accordingly also. So maybe if something eventually fails and you start to look back, not all the data of the second kind that I'm talking will be relevant in figuring out, right?
So I think what you're saying, I'm not sure I understand the question completely, but I think what you're saying is, as we go along and we skip a bunch of tests, we get a result and say it's a failing result, and we go back and fill things in, the code is different, there's all kinds of variation under the covers there.
Right.
That could mean that we're not getting the same result, the same execution path for the test. Again, as testers, we kind of make a assumption that the system is stable, and maybe it's not. So in cases when we culprit find, say, a flaky test, it could not really, there isn't a culprit to find. We just go back and we find more flakiness. And yes, that happens. our system doesn't cope with that very well. We try not to culprit find flaky tests. In fact, any test that we've observed to be flaky, we just exclude it from culprit finding. But again, the tests aren't changing at a rate. Each individual test is not changing anywhere nearly as often as we run them. So we kind of make the simplifying assumption that a given test with a certain name is more or less stable. And we track them only by their name. That's what we know, the name and the pass-fail result. We don't look at the content. We don't keep an MD5 checksum. We don't tell whether it changed, whether any of the code that it tests changed. Yes, and for both of those two questions, the earlier one, they're both kind of related. It is true that we make some simplifying assumptions in that area.
And the frequency, I think, helps with that assumption. So every 45 minutes, this is running.
Yeah.
So you get lots and lots of results in a day.
Yeah, we record 20,000 QPS of pass-fail results.
So I have a two-part question over here. Very insightful information overall from a test results analysis perspective. So the test data here, is it a combination of unit tests, integration tests, UI tests? And then the second question is, how do you draw a dependency graph between a code change and a unit test and an integration test and a UI test?
All the questions are hard.
They're all hard questions. So I think most of the tests that TAB deals with, I'm going to say this, and you can correct me or not, are unit and integration tests. Very few end-to-end UI tests in this, if that helps.
Well, also the sort of, we limit test run execution times to 15 minutes. We also limit tests to hermetic tests. And our build language, which we have an open source tool called Bazel. It's also been ripped off by Facebook and by Twitter. They have a buck and a, I can't remember what the Twitter one's called off the top of my head, but
This is being recorded.
I know it is, that's fine. They know they did it. There's probably a Facebook person here, they're probably gonna yell at me. But this system records dependencies between every test and what it depends on. And in fact, we sandbox every execution of anything so that we're absolutely certain that we've captured all the inputs that it uses and all of the outputs that it produces. That's a fundamental property of the Blaze build system, which externally is called Bazel, or the Buck system, or the Pants is the Twitter name for it. But it's kind of the same thing. All the tests are in the build files. They're part of the build rules. They depend on the executable binary and whatever data files they need. They have to declare those. So that's how we have good, clean dependencies so that we can use this reverse dependency map to trigger the tests when they're supposed to run.
Okay, one last question, Eric. I think you have one over there.
Yeah, I guess it's kind of tied to what they said there. There are some teams that don't have the luxury of unit tests or that analytical connection between the test and the actual code. So what are you suggesting in that case? Should they go and invest in code coverage tools that would allow them to get that delineation and the minimum distance that you're talking about? Because it sounds like what you are saying is you ought to invest in unit test cases such that you know that you have a definitive minimum distance that is quantifiable.
Well, it's an interesting point. I mean, it depends on your level of sophistication, right? And your size. At some scale, you could just run every test every so often, and it's probably good enough for a small team, for a small group. I mean, we're talking 30,000 developers committing to one branch. It's a very different situation than depending on your thing. But as you climb that sophistication ladder, yeah, I think, you know, being able to record your test history is pretty important. Being able to understand and analyze flakiness becomes really important. As you start even just getting to moderate size, you don't necessarily need to do test selection. In fact, the Netflix guys came up with a sort of, for them, and they have a pretty big team, kind of a pretty good way of doing test selection. They just said, oh, there's a group of tests that we run as pre-submit, and there's a bunch of tests that we run as post-submit, and we manage the list manually, and it works for them. So I encourage you to move in the direction, okay, but you don't have to get to where we are right away. That's not the first place to go. In fact, I wouldn't even recommend that unless you're getting to be pretty large and having a lot of pain. So, but I do think that what we did, one thing that I think is totally absent from the state of the art, which really bothers me, is this ability to just record the individual pass-fail results of your test cases. Super important. It was very, you know, just looking at that data, it can help lead you to certain things, like how flaky are your tests, or How often do developers break things? And those statistics are super important to improve your development process. And having data to analyze is a step in the door for someone like Atif. I threw him a couple of terabytes of data. I said, go figure out what's there, And if I didn't have that data, none of this would have been possible, right, for us. And whatever size you are, I think some of that data-driven approach is a good one. That's just me. I've kind of preaching a little bit there because it's important.
So another feature that was very useful for me was that if I wanted to find out if this test case that was never run a month ago, what its result would have been, I could actually get Google to go back a month and run the same test on that code that was a month old, and it would give me the same results as if it would have been run that time.
Yeah.
Right. Thank you very much, Atif and John.